Hello, my name is Saif Ali Khan, and this is my final project for CSCI S-89, Drug Side Effect Prediction Using Deep Learning. The goal of my project is to demonstrate how deep learning can be used to predict potential side effects of drugs based on their chemical structure, using data from the CIDR side effect resource. Adverse drug reactions, or ADRs, are a leading cause of patient risk in clinical trials and even after drugs are approved. Detecting side effects earlier can not only reduce patient harm, but also save significant time and cost in drug development. Traditional methods often mix complex patterns. Deep learning provides a way to identify nonlinear relationships between chemical structures and adverse outcomes that simpler models can't capture. The challenge is that side effect prediction is a multi-label problem. A single drug may cause many different side effects, and there is strong class imbalance. Some side effects, like nausea, are very common, while others are more rare. The relationship between drug structure and side effects is highly complex and nonlinear, so the question I want to answer is, can a deep learning model learn these patterns well enough to predict side effects reliably before clinical trials? For this project, I used the CIDR dataset along with chemical information from the Stitch v5 database. After cleaning and merging, I obtained 1,289 drugs with valid SMILES chemical structures, 4,115 unique side effects, with 87.5% drug coverage after processing. Each drug is represented by its name, a 2048-bit Morgan fingerprint derived from its SMILES string, and a list of side effects using med-DRA preferred terms. The data pre-processing pipeline is shown here. First, I filtered CIDR to include only med-DRA preferred terms, which are standardized side effect labels. Next, I joined in drug names and chemical structures from Stitch v5. Then I used RDKit to convert SMILES strings into 2048-bit Morgan fingerprints, capturing substructures of each molecule. Finally, I used scikit-learn's multi-label binarizer to encode the side effects into a binary matrix. This gave me the input matrix X of size 1289 by 2048 and my output matrix Y of 1289 by 4115. The model is a feed-forward deep neural network designed for multi-label classification. The inputs are 2048 features from Morgan fingerprints. Hidden layers are a dense layer of 1024 units followed by dropout, then another dense layer with 512 units and dropout. Output is 4115 sigmoid units, one for each possible side effect. The loss function is binary cross-entropy and the optimizer is atom. I also used early stopping and model checkpoint to avoid overfitting and to save the best model automatically. Taking a look at training performance, here we see the training and validation loss curves. Both loss curves drop steeply in the first few epochs, showing the model quickly learned meaningful patterns. Validation loss stabilizes early, and the gap between training and validation loss stays small, indicating the model generalizes well and does not overfit. For evaluation, I used ROC-AUC and PR-AUC instead of accuracy, since this is a highly imbalanced multi-label problem. The results are as follows. Macro ROC-AUC 0.65, micro ROC-AUC 0.87, macro PR-AUC 0.2, micro PR-AUC 0.41. The high micro ROC-AUC shows the model performs very well on common side effects, while the lower macro PR-AUC highlights the difficulty with rare effects. This histogram shows the distribution of ROC-AUC scores across side effects. Many side effects are predicted well, with ROC-AUC above 0.7. However, there is a long tail of rare, harder to predict side effects with lower scores. This imbalance is why we need both macro and micro metrics. This is a heat map of predicted versus actual side effects for a sample of drugs. White cells indicate correct predictions, Green cells are false positives, where the model predicted a side effect that was not present. Red cells are false negatives, where the model missed a side effect. You can see that common side effects tend to be predicted correctly, while rare ones are often missed. The model demonstrates several strengths. It can handle thousands of side effects simultaneously and achieved a high drug coverage at 87.5%. It shows strong predictive power for common side effects, and it's easily visualized with heat maps and ROC-AUC distribution to help explain its behavior. However, there are also some important limitations to take note of. Rare side effects remain difficult to predict. Morgan fingerprints capture 2D chemical features but miss important 3D structural information, and the model's interpretability is limited. It's still a black box. The model also depends on having SMILES data available, which may not exist for all drugs. There's plenty of interesting future work that I'd like to conduct. First and foremost, I'd like to explore graph neural networks, which can directly model molecular graphs instead of using fixed Morgan fingerprints. I would also like to apply techniques to address class imbalance, like using focal loss or weighted binary cross-entropy. I'd also like to integrate biological target information like gene or protein interactions. And lastly, experiment with transfer learning from larger chemical property datasets to improve rare side effect prediction. In conclusion, this project shows that deep learning can be effectively applied to side effect prediction. The model performed well on common side effects with high micro ROC-AUC. The challenge remains in predicting rare side effects, which will require more advanced methods. Ultimately, this approach has the potential to improve drug safety evaluation and risks before clinical trials. It just needs further development. For this project, I used data from the CIDR and Stitch databases, along with RDKit for chemical fingerprints and TensorFlow Keras for deep learning. Thank you for watching, and have a good rest of your day.